Hello, my name is Luis Orbe. I'm the Customer Support Coordinator for Photonic Solutions. Today, I will present you a brief introduction into the methodology to design and simulate Metalens by using RSoft photonic device tools and Code 5. In this session, I will start with a brief introduction on what is a Metalens, why to use a Metalens, and how to design and simulate it. Then I will provide some details on how to simulate a nanocell, which is the building block of the Metalens. After this, I will explain the design procedure for the simulation of the whole Metalens. For this, I will do it by covering two approaches, the direct simulation or through a transfer function mask. This presentation will then explain and validate each one of them, and then we will end with a summary of the most important points. First, what is a Metalens? So according to the definition found in literature, Metalens is a lens made from a metamaterial. But then, what is a metamaterial? Well, according to the dictionary, it is a synthetic composite material with a structure such that exhibits properties not usually found in natural means, specifically a negative refractive index. So, the metamaterial is a nanodevice, not the conventional material per se. On the left are so-called negative index materials, which refracts light in the opposite direction. And we also have a metamaterial mirror, which reflects light selectively. Both theory and experimentals show that subwavelength nanocells can shift the phase, well, in this case, of the light that goes through them. Different shapes and sizes of the nanocells can produce different phase delays, and on the right side we can see this being demonstrated by the researchers at Purdue University. Another question we can do is, why are Metalens necessary, or what problem do they solve? Well, we may or may not realize that microlenses are widely used. They are basically everywhere, from image sensors to LCD projectors. However, it is very difficult to bear curved microlenses, especially if they require, well, a very accurate curvature. And of course, this is a very complex procedure. Metalens, on the other hand, well, it's a flat surface with a 2D nanopattern. So you can do this with a single etching step, so it's suitable for mass production and cost reduction. Now, of course, from a research point of view, there are many different technologies to make Metalenses. 3 of them are showing the most potential for mass production. The first is nano imprint. This is more like making a waffle, except in the nanoscale. This is considered a new technology compared to others, and the exact shape is harder to control, so it can be used for lower requirement applications such as image sensors, LCD projectors, etc. A more mature technology is plasmonic lithography. On this, nanostructures can be duplicated by using a pre-designed mask. The accuracy of this is quite high compared to nano imprint, but of course, the most accurate technology, and the third one in our list, is electron beam lithography. This is mass-free, and the pattern is computer generated. The tolerance is, well, in a few nanometers, so it's suitable for making high-precision Metalens. For example, those included in imaging lenses. Well, with this introduction, the next question is how to design and simulate a Metalens. Because of the nanoscale, the phase shift of the nanocell must be calculated by using a rigorous algorithm, such as FDTD, FEM, or finite element method, or RCWA, which is rigorous coupled wave analysis. For the whole Metalens, however, none of the above algorithms is suitable because they all require a lot of computer memory and they take a lot of time to calculate. So this means they can only be used to simulate very small structures. Now to solve this, we have other options, such as using BPM or beam propagation method. Of course, we have validated the BPM results against FDTD for a small structure. And later we did that for BSP for a large structure. But of course, being fast comes with a price. BPM is one-way propagation, and it cannot account for backward reflections. In case the reflection of resonance in the nanocells is important for you, then BPM will not be accurate anymore. So for that, we are proposing another approach. We call it the transfer function mask, or TFM. First, we can use FDTD or RCWA for nanocells to form a TFM of the whole Metalens. Then we grab that TFM and we use BPM to propagate the transmitted field in a free space where there is no reflection at all. Sounds good. But first, let's see how to simulate a nanocell. In this slide, you can see an example of a nanocell with a rectangular lattice. In this example, we set up 4 monitors. A special monitor to record the field distribution inside the nanocell, then a special monitor at the end of the length of the nanocell to record the field distribution. Now we make this to make sure the computation domain is big enough for the input wave to go forward and then, well, to get reflected. A single value monitor is put at the end just to record the power, not the amplitude, because the amplitude can be bigger than 1. And of course also to check for the phase of the transmitted field. Another single value monitor is put at the beginning position to record the power and phase of the reflected field. Now the simulation engine can be FDTD or RCWA. Now when doing this simulation using full wave FDTD, we can obtain the following results. In here we can see that the spatial output on the XZ plane shows the field distribution inside the nanocell. The other spatial output at Cmax position, or in this case at the end of the device, shows the field at that position, which is far enough to ensure the field distribution is uniform. Both power and phase outputs are recorded into a file and can be plotted by beam plot. Now, in case we do the simulation by using diffrag mode RCWA, all the outputs are exactly the same as in full wave FDTD, except that the results are going to be stored in a file with a different name. They are even in the same order as shown in the computation window right there. Now, of course, once you have the results over there, you can run an optimization procedure using most to read the phase for the file. This is in case that you want to use this information for other applications or to further define or optimize your design. But first, let's take a look at the simulation of the nanocell. In this example, we simulated 2 types of nanocells, nanopillars and nanoholes. So as shown in the charts, either nanopillars or nanoholes cause similar phase shifting, but the nanopillars give a positive phase shift, while the nanoholes give a negative phase shift. Well, this is very obvious, since any medium has a higher refractive index than air. More medium, higher index, more air, lower index. Now, when testing the 2 different lattice patterns, hexagon and rectangles, the results will show that the lattice type doesn't really affect the phase shift. What really matters, or what is really being affected, is the filling factor, so basically the size of the nanocell. So you now might be wondering if there are any difference if I use full wave FDTD or diffrag mode RCWA to simulate this. So to answer that, we made a simple test with using this nanopillar structure. So here you can see that we are calculating the reflection by both of the tools and the transmission on the face, of course. So as we expected, full wave FTTT and diffract mode RCWA, they both give almost identical results. Now we also notice some very minor discrepancy, especially because of the numerical algorithms, and at the end, well, these are very different approaches. But in any case, we saw difference, right? So how do we decide which approach to use? Well, in this case, the problem will need to be studied because different characteristics like the symmetry of the nanostructures or the size could be things that may affect going into one algorithm or the other. Now let's talk about the Metalens design procedure we propose. For this, we will explain step by step. In step number 1, we obtain a phase shift curve for a certain web length by using a Mohs scan of the size of the nanocell. So for those asking, the actual size of the nanocell is the diameter of the pillar. After this, we normalize this result by the lattice constant. The direct output is wrapped phase within 360 degrees. To use this design as a curve, we need to further unwrap the phase to make it a single value function. So this is done in this example by using WinPlot, but it can also be done easily with RSoft Python library. Now on step 3, on the right side, we reverse the function to make the diameter as a function of phase. So once again, this can be done in WinPlot or by using the RSoft Python library. After this, we choose the proper range of the diameter. For doing this, it should be manufacturable and cannot be too small or too large either, but should be large enough to provide more than 360 degrees phase shift. Step 5 on the bottom right, the design target plays a role. Depending on the application, the phase profile can be different. Here, we use an imaging lens as an example, and the phase profile should satisfy this function in order to the light to focus on the focal point. Based on this phase condition, we are then able to create the ideal phase mask to achieve the design goal. This is shown in step number 6. The last step, or step number 7 on the bottom left, is to write a script that helps us find the required phase at any given position. After this, we need to determine the corresponding size of the nanocell. For example, for this position, we read the phase required, then we locate its position on the design curve, and then we find out the size of the nanocell which can generate a phase shift of that magnitude. Then we place it at the position we are working on. So by doing this, we can get the layout of the whole Metalens cell by cell. Now that the physical mask layout is in place, the transfer function mask, which includes both the transmission amplitude and the phase profiles, can be generated for the different wavelengths and polarizations. This, of course, taking the transmission characteristics of the nanocells as base. The detailed procedure goes like this. Starting with the physical mask, for each nanocell we can find its corresponding phase shift for different wavelengths. Then we can create phase profiles for each of them. In the same way, we can find their corresponding transmission amplitudes for the different wavelengths to create different amplitude profiles. After this, we can combine the amplitude and phase profiles into one file, creating a so-called transfer function matrix, or TFM. This, of course, happens for each of the wavelengths. Since the nanostructure maintains a 90-degree symmetry, this is not polarization dependent. Otherwise, we will have another 3 TFMs for the other polarization. In order to do simulation in RSoft photonic device tools, we first need to complete the layout of the structure in RSoft CAD. An IND extension file can be generated for different lattice patterns. This can be done by using a Python script, and this is of course based on the face mask. On the left side, you can see a piece of the Python code we used to generate the layout. This same script can be easily modified to support both rectangular or hexagonal lattice filters. You can see both examples right here. Once the simulation results are satisfactory, we need to send it to a foundry to have it fabricated. The common file to do this is the GDS2 extension. This file is generated by RSoft CAD, but it can also be automated. So this file is or can be generated without a GUI. After this, we can obtain the GDS2 layout of the whole lens. If we zoom in, we can see all the details. You can see this on the right side of the screen. Now it is time to move on to the simulation of the whole Metalens. But let's first talk about the direct simulation, which means using PPM to propagate the light through the nanoarrays. On this first example, we test a small lens with an f equal to 20 microns. We also consider a plane wave input that goes through an aperture. In this slide, you can see the layout and simulation results when the aperture size is 10 microns. However, as you can see, the calculated focal length is 16.1 micron, which is quite different from the theoretical results. To verify, we use FDTD, but we found out that the value for the focal length was quite similar to the PPM result, which means that both results do not really agree with the theoretical result. So this is telling us there are some external design considerations that are not being taken care into account. So what is happening? The answer lies in the pinhole effect. In this slide, we show how different input fields behave when they are not taking into account this effect. This confirms that our suspicion that the approach we took so far is incomplete. Indeed, a small hole can form an image and behave like a focusing lens. That explains what happened to our simulation results, as we initially designed a lens with a desired focal length. If the aperture is too small, the pinhole effect shows up, and it is equivalent to add a focal length and make the overall focal length way shorter. To prove the theory, we redid the simulation for a real lens. What we're doing here is to change the computation window, which is the same as to vary the aperture size. Shown here is the PPM simulation result. As observed, when the aperture is small, the focal length is indeed shorter than the design value. As the aperture size increases, the result approaches the theoretical result. By checking this, the extra focusing of the aperture, due to the diffraction at the aperture edge, has to be taken into consideration when you are doing a small lens design. When we took this effect into consideration, the simulation gives a result that is now very close to the theoretical results. To further verify, we ran the simulation using both PPM and FDTD algorithms again, and in both cases, the results very close to the theory. Now that we understood the effects at a small scale, we are moving to a big lens with an f of 200 microns and an aperture distance of 100 microns. For this, a simulation using a plane wave input gives a simulated focal length of 198 micrometers. However, when we switch to a Gaussian input, we got an even better result, 200.1 micrometers. So, with these results, we can claim that BPM simulation is very accurate. And compared to the theoretical results, both numbers are almost identical. So from this point, a valid question would be if can this structure be simulated on a different way? It is definitely way too big for FDTD, but what about ray tracing in Code 5, which is a different imaging lens design software also from Synopsys? So that's what we did. We ran a ray tracing simulation through the face mask interface. The results show a focal length of 202 microns. So in this example, ray tracing gives a very good result for this well-focused length. And it was actually more efficient. At this point you may wonder, why are we not considering ray tracing for the entire simulation? That is because of a basic limitation of the ray tracing methodology. It cannot handle coherence. In addition to this, the dispersion curve of the nanocell adds a little bit more into the issue. At the design wavelength, which is green in this example, the nanocell range we choose can provide a 360 degrees phase shift. Within the same range, the phase shift for red and blue colors are either too little or too much. At the design wavelength, the grabbed face of the lens is the same as a Fresnel lens. The ungrabbed face forms a smooth face profile. So that means that when an input with equal phase is passing through, every ray behaves well. No diffraction can be seen and all light from all components focus at the designed focal point. However, when we change to a different wavelength, the unwrapped phase is not as smooth anymore, and the light from each segment will interfere with each other. In addition, diffraction effects at the phase junctions make things even worse. Unfortunately, those coherent phenomena cannot be accounted by ray tracing. So with this, we turn to a different algorithm, BSP. BSP stands from beam synthesis propagation, and is a beamlet based propagation algorithm that is used by Synopsys Code 5. This is modeled also in physical optics. Now, since BSP cannot deal with the nanostructure, the phase masks we generate for the three different wavelengths are used in the simulation. After this, we got the focal length as well as the field distribution at the focal point for each wavelength. If we were to compare them in a table side by side, we will see that BSP results are very close to the BPM results. Now let's check on the polarization dependence of a different structure, such as nanofilms. Shown here are both the phase and the transmitted power. As we predicted, the nanofilm is polarization dependent. So this means the transfer function mask that is based upon it is 2. However, the simulated focal length is not that off, only 1 micrometer away. With this, the BSP simulation algorithm also confirms the BPM result. So at this point, we can draw a short summary that: number 1, a nanofilm-based metalens is polarization dependent, and number 2, the TFM approach can simulate the polarization dependence very accurately. Based on this, we can also say that the BPM propagation algorithm through a transfer function mask gives accurate results. Actually, quite similar results to what you obtain by using BSP. We can also state that BPM propagation through nanoarrays gives reasonable results in case there is little reflection. Unfortunately, it doesn't give very good results in case there are strong reflections or resonance. So with this, we are near the end of this presentation, and let's just draw some conclusions. First, we demonstrated and talk about an effective simulation methodology for Metalens. We use a number of methods to both apply the design and then verify the accuracy of this design against the theoretical numbers. To the best of our knowledge, this is the first attempt to simulate a large whole Metalens systems. We also find that by using this method, we can predict the polarization dependence and the dispersion of the Metalens system. We also see that the results show that this method is accurate and is also very efficient. And of course, this algorithm this entire methodology can be applied to any metasurface in imaging systems. So with this, I would like to thank you all for joining this session, and now we open the floor to answer all the questions that you wrote us during this session. Thank you very much.